Welcome back. In this clip, we continue our presentation of high-temperature geothermal systems, that is, systems which tap into very hot fluids that are used to produce electricity. Building on the general features we presented in the previous clip, we will show two specific case studies, Iceland and Larderello, two systems of great importance in the geothermal world. Iceland is a powerhouse of geothermal energy, where the greatest technological challenges are being addressed, such as drilling at temperatures above 450 degrees. Iceland, a country which is nearly self-sufficient in terms of energy production. The second case study is Larderello, a small locality in central Italy. Known already from Roman times, Larderello is the oldest geothermal system used for industrial purposes. For both systems, we will discuss the geological setting, the geothermal system, and how energy is extracted and the associated challenges. Iceland is located on top of the mid-Atlantic oceanic ridge, which is the boundary between the European and the North American plates. These plates move away from each other at rates of a few centimeters per year, allowing for the continuous creation of oceanic crust between them. In this more detailed map, you see the mid-oceanic ridge traversing the island in north-south to northeast direction. A large number of volcanoes is associated with the ridge. Masses of partly molten intrusive rocks will be present underneath them. If you look at the distribution of geothermal plants, you see that their position is aligned with that of the gravens. There is little doubt that extension and magmatism control the distribution of these very efficient and productive high-temperature thermal systems. The segment of oceanic ridge forming Iceland has been pushed upward by a mass of hot and partly molten material which has been identified underneath the island. This hot body of rock is visible in the map of seismic velocities underneath Iceland. The red colors in the section indicate masses with lower than normal seismic velocities, which correspond to higher temperatures. And this is what the uppermost kilometers of the crust look like. Magmatic intrusions are very close to the surface and impose a very high geothermal gradient. Meteoric waters enter into the system, are heated, and start moving upward, typically along faults. The yellow line in the diagram indicates the depth at which waters reach a supercritical state, which means that even at high pressures, water is too hot to stay in a liquid state. At 22 megapascal pressure, this temperature is around 375 degrees. Iceland did not leave the challenge of drilling at these incredible high temperatures and launched the Iceland Deep Drilling Project with the aim of drilling into the volume of supercritical fluids. In a way, results went beyond expectations. The IDDP drilled through the supercritical volume and reached the magma chamber, an amazing performance. The attained temperatures around 450 degrees, however, were too high for the material involved and the drilling was stopped. The Hellisheidi plant gives you an idea of the size of the operation in Iceland. Hellisheidi is the third largest geothermal power plant in the world. From its 50 wells, it produces 300 megawatts of electricity and 133 megawatts of heat used for the Icelandic capital, Reykjavik. A 90% load factor, this covers the electricity needs for 480,000 households and heats 80,000 of them. As a comparison, consider the largest offshore wind turbine present available, which produces about 12 megawatts of power. But to do this, does this up to 50% of the time. A geothermal power plant produces energy for more than 90% of the hours in a year. Look what Iceland has achieved during the last decade. Geothermal has become the dominant source of energy with some integration with hydropower. A very minor portion of energy is provided by fossil fuels, mainly for transportation purposes. Geothermal covers nearly 90% of the heat needed in Iceland, despite the very cold temperatures of this island. Having satisfied most of the energy needs, Icelanders are thinking of new ways to use the huge amount of energy which there's still in the ground. For instance, developing energy-intensive industries such as aluminum processing plants. And here we come to our second case study of high-temperature geothermal systems, Larderello. The Larderello geothermal system is located in the Italian Apennines, the upper plate of the Adriatic Plate subduction zone. In association with the subduction zone, extension developed, creating the Tyrrhenian Beck-Arc Basin. The combination of subduction-related magmatism and extension is the main reason behind the very high temperatures observed in Larderello. Young volcanoes with associated magmatic bodies document the intense magmatism of the Larderello region. In this cross-section, you see the subducting Adriatic Plate and the Beck-Arc Basin developing on the upper plate and forming the Tyrrhenian Sea. The magmatic province hosting Larderello is located at the boundary of the extensional domain, there where magmatism is particularly intense. The crust underneath Larderello is quite thin, in the order of 20–22 kilometers. Magma derived from the mantle forms magmatic intrusion at depths of a few kilometers. In seismic data, a prominent reflection is visible called Horizon K. Scientists interpreted Horizon K as a zone of intense shearing forming the top of a zone of partly solidified magmatic bodies and of very intense high-temperature gas circulation. A more detailed section shows the top of the intrusive body very close to the surface. The isotherms predicted for the system show the very high gradient present in the area. And here you see the wells which have been drilled into the system, reaching quite high temperatures. Larderello is the oldest geothermal plant in the world. In 1904, the Prince Piero Ginori Conti showed that it was possible to generate electricity and to power a few light bulbs from geothermal energy. In 1913, the first generator was in place with a power of 200 kilowatts. Electricity was used then to support the chemical industry associated with the site. In 1970, fluid reinjection was started in order to keep aquifer pressure and dispose fluids. Larderello currently produces almost 1 gigawatt of electricity, covering nearly 25% of the consumption of the region of Tuscany. Larderello still has a great potential. Future challenges are mainly drilling into the zone of critical fluids. Quite a dangerous adventure to be modeled and planned with great accuracy. High-temperature geothermal systems are located in areas with very high thermal gradients. These are found in zones of intense extension, magmatism, or combination of both. In these cases, high temperatures can provide large amounts of electricity and heat, thereby provide a major contribution to renewable energy. Major challenges lie ahead of high-temperature geothermal systems, such as increasing the efficiency of flow and drilling into the zone where fluids are at the supercritical state. The future will surely bring interesting news.